do you find that you learn things a little better when you get to see a picture or an image of the real piece of equipment that you're trying to learn how to analyze? So to go from formulas, or more, I would prefer the word fundamentals, to go from the fundamentals of analyzing equipment into the real world, you're going to learn it a little better if you can see how what things might look like that you're learning how to analyze. And so in this section, what I'm calling this in section chapter 8, basic components of the Rankine cycle. And I'd like to just take a little time, and it will take some time, to go through and show you some images of what the four primary pieces of equipment associated with the Rankine cycle look like, and try to give you some operational ideas of what they're doing. So remember what we've got here. Here's our basic Rankine cycle sketch that you'd be able to sketch on your own. The boiler, the turbine, the condenser, and the feed water pump, and they're all hooked together in order to make electric power and to comprise a system operating in a cycle at a steady rate, kilowatts, megawatts, horsepower. So we're into section 8 called the Rankine cycle. Here's an image. Oops. Sorry about that. I was clicking around and looks like I paused my sharing. This is an image of the John Amos power plant in Winfield, West Virginia, which is just west and a little bit north of Charleston, West Virginia, located on the Kanawha River. And so one thing you think, well, why is it on the river? That's going to be the source of cooling water. And so as you see this, you see three exhaust stacks, you see three cooling towers. This stack here, I believe, is an environmental controls related stack for cleaning the exhaust. But basically, you see three units. And sure enough, when I go to Wikipedia, I see that these three units each are rated at about 1,000 megawatts of net output power each. And so what you're looking at in this image is about 3,000 megawatts of electric power running 24/7. So that's enough to blow your mind. This is a huge facility. I've driven by it. I've not been in it, but it is absolutely huge and employs probably, I'm going to guess, maybe 1,000 employees. So this is what a large-scale steam power plant looks like with three separate units. And so what are the benefits of making electric power using steam power plants, using the Rankine cycle? Well, continuous operation. So working with this H2O as phase change fluid, this enables us to run 24/7, 365 days a year with minimal downtime due to maintenance. It enables us to react to changes in electrical power demand. So remember that power plants, they have to simply meet a demand. They don't run and store up energy somewhere. They've got to sell the energy, or that electric power has got to be used as it's produced. So real quick overview of heat sources. Well, natural gas, that's a fuel heat source. And it turns out that you'll see, I hope, in the images, a boiler running on natural gas has the ability to quickly respond in changes in electrical demand. A coal-fired plant using coal as the fuel is slower to respond. It takes more time to speed up or slow down in terms of the rate at which you're making power. Now, when I say speed up, it doesn't mean you're changing the frequency of electric power. It just means you're speeding up your heat input or slowing down your heating input. And finally, nuclear power heat source is even slower to respond than coal as a heat source. And so that's going to give you a physical feel why in the electric power industry, we use different sources of heat because of the need for responding to the demand almost in an immediate manner. So thus there's a diversity of heat sources, and you have to address that during the design phase of your power plant. you can't just go and decide to change fuels out overnight. How about some disadvantages? What are some drawbacks of steam plant operation? Well, when you have fuel, you've got exhaust gas. So you put in fuel and air, and to get that heat, you're going to have exhaust gas as a result, and it's going to be discharged to the surroundings. It needs to be treated, but certainly there are issues associated with physical pollutants. And also there's issues talking about climate change. And so those would definitely be considered drawbacks. Now, that's on the exhaust gas side. How about the heat rejection side? We don't even mention heat rejection in our thermal efficiency, do we? But heat must be rejected to the surroundings. So you've got two choices when you're running a steam plant. Either you can have a cooling tower operation, kind of like what you saw in that image of the John Amos plant, where heat is rejected to the atmospheric surroundings by way of a cooling tower. You saw that big plume of steam vapor, right? So that's just evaporate. That's cooling water that's being evaporated into the air. Okay, or you can reject heat directly to the lake or a river or the sea, and you will be rejecting it back at a higher temperature than you got it from. And so that would be a drawback as well. And so on the John Amos plant, that's why you see a combination of being located on the river and having cooling towers. So cooling water is needed. That's why we need a big supply of cooling water from the river, and heat is rejected by way of the cooling towers and into the river as well. Let's go through and look at some of the details about each of the four major components of a steam power plant. So the first is a steam generator. Purpose is at constant pressure, transform boiler feed water, compressed liquid, into superheated steam vapor by way of high temperature heat addition. And so for all steam generators, what do they have in common? Well, they all have in common a high temperature heat source, which could be fuel and air with the byproduct of an exhaust gas, or for a nuclear power plant, the heat source would be the reactor heat release. So everything is in common is the high temperature heat source, and heat is, so look in my sketch, I'm trying to show Q dot H, heat flowing into this steady state, steady flow open system called a steam generating unit, one inlet and one outlet. And so I'm hoping that this gives you an idea of, although boilers can look very complex and complicated, this is what's going on from a high level standpoint and your analysis expertise, which is getting better and better. I'm going to start you off with the most simple example of a steam generating unit or a boiler, and that's it's a packaged natural gas fired boiler. Manufacturer of this particular boiler is Babcock and Wilcox. For many years, they were located in Lynchburg and also in Ohio, I think in Columbus, Ohio. And so the idea, you see a bunch of tubes, right? And so what we've got going in here is, well, let's look at feed water. Feed water is admitted into the boiler, and it goes through these tubes, and actually the compressed liquid circulates through these tube banks, and the hot exhaust gas boils that water, and it turns it into a saturated vapor. And that's why we have this long cylindrical thing here called a steam drum, because as the water circulates around and around and around and becomes saturated vapor, because of gravity, rises to its highest level, and the saturated vapor is collected in this steam drum up high with the saturated liquid below. So there'll be some level in this steam drum where you can actually see with a sight glass where's the saturated vapor and saturated liquid. You can see it with your eyes. Okay. And then finally, coming out of the steam drum, it goes into more tubes. The saturated vapor goes into more tubes where it's further superheated. And so I've tried to show that here in what we call the superheater section. And then off it goes to the steam turbine. On the fuel side, natural gas is going in to this burner head. Air is admitted around the burner head. That's where the combustion happens. Very high heat release. And so the exhaust gas then is what is responsible for the Q dot H. The combustion process and the exhaust gas is what comprises the heat transfer. And you might say, well, what's the size of this thing? I have been and have started up these types of boilers. It turns out that this is ground level here. So if you're standing at ground level, this natural gas burner is right at eye level. And so it's not the biggest thing in the world. It's really a pretty compact unit. And so from ground level up to this natural gas burner might be 6 to 10 feet high. So really not that big. Now, this is an example of a huge piece of equipment. This is an example of a pulverized coal steam generating unit. So this would be much higher Q dot, much higher mass flow rate than what I showed you coming out of that packaged boiler. So probably many times greater, both on the Q dot H side and the M dot steam side. And so let's see what we have here. Well, we have feed water going in, and it turns out that even for this large unit, we have many thousands of boiler tubes where the compressed liquid is circulating through there. It's receiving heat transfer. It's becoming a saturated vapor. And as it becomes a saturated vapor, it gravitates towards this steam drum. And so in color, you can kind of see the depiction of what's higher in the steam drum is saturated vapor. What's bluer would be saturated liquid. And so that's circulating around through the walls of the boiler, and the walls are made up of vertical tubes. Okay. That saturated vapor then goes out, and now you see that it's sort of following a tortuous path of tubes called a superheater. So the superheater tubes is what enables the saturated vapor to become superheated vapor. And so, as in my sketch here, superheated steam goes off to the turbine. Okay, and so you get the general idea. We've got coal coming in here along with air, and that's where you're getting your flame. Very high. So you can see with your eyes. Now I think I see what the high temperature heat source means. Here's an example of what's called a fluidized bed steam generator. Could be about the same order of magnitude size as that pulverized coal steam generator. Down here at the bottom of this picture, there's a person. There's a person standing on the ground at the foundation of this boiler. So that's going to give you a physical feel for the size of the steam generating unit. It's huge. Fluidized bed. Well, the type of material that could be coming in as fuel could be what we call biomass, limbs, old leaves, things like that, wood chips, and sawdust. So this is a very common type of fluidized bed steam generator fuel. Also, coal can be used, but nowadays, I think you're going to see that these types of fuel sources are used in fluidized bed steam generators. Same idea. Let's see what's in common. Well, we've got air coming in. I'm sorry. Where's our feed water? Feed water. I'm looking for feed water. Here it is. Bottom left. Feed water's coming in to the circulating tubes. So it goes through these thousands and thousands of water wall tubes. Here's that same steam drum idea. And then once the steam is transformed into saturated vapor, off it goes to the superheated section to be further superheated at constant pressure, and then off to the steam turbine. Okay, hope that's given you an idea of what a lot of this equipment looks like. There are, such as the John Amos power plant, a number of large power plants operate at supercritical pressures. And this is a screenshot of one of them. The same general idea. I didn't circle my person, but I'm going to use my cursor over here. But you see that little dot over here on, that's a person. So I believe that's a person. And so it gives you an idea of the scale. And then here is a photograph of in Texas of a supercritical boiler. Texas, the weather is so mild that it doesn't have to be enclosed in Texas. But the idea here is if we look at this picture, I don't see a steam drum anywhere. No steam drum. And that's because for supercritical pressure, boilers that operate at supercritical pressure, the transition point into superheated vapor is hardly even visible because you're adding heat and you're never passing through the vapor dome. So that is a very interesting and has been high-tech situation where you increase the pressure of the feed water so high that the working fluid H2O never gets into the vapor dome, at least from the feed water during the heat addition process. I sort of misspoke. Now on the condensation process, certainly it's under the dome, but on the boiling process, the feed water never gets under the dome. It stays above the dome from compressed liquid all the way to superheated vapor. So that's so supercritical boilers are real and are commonly observed. When I came back to teach in 2021, 2022, I had a lot of interest in what kind of fuels do we have nowadays? And I discovered this website run by the US government called the Energy Information Administration, EIA.gov, and it is a gold mine of data. Okay, and so it is the facts. And so in 2022, I got the most recent available data, and it's from 2021, and say, what are the fuel sources for steam power plants in the US? And here's the results. Look at this. 38% natural gas, 22% coal, 19% nuclear energy, 11% what it says renewable, non-hydro, non-solar. So that would be like biomass, wood chips, sawdust type idea. But then there are other small amounts of sources of electric power. So obviously hydropower would be kind of like Smith Mountain Lake. But the point I'm trying to make is that at least in 2021, the heat input sources for electric power plants is about 80%. So natural gas, coal, and nuclear are responsible for about 80% of U.S. electric power generation. So anyway, those are the facts. That was the steam generator part of this video. Let's move on to steam turbines. What do steam turbines look like? Well, here is an image I'm very proud of. It's a cutaway view of a multi-stage industrial or commercial steam turbine. And so let's look at that. Well, notice how all these stages, they're all driving one single shaft. That's one thing important to realize. Here's the electric generator. Because we're going into the high pressure turbine at very high pressure, here is a seal. We have to seal the shaft off from the surroundings. And so this pretty complex looking thing is the labyrinth seal that seals the high pressure steam away from the surroundings so we don't have leakage. Going the other direction, well, this is our high pressure turbine section. And now you say, oh, okay, I see that steam is going through, steam is expanding, we're making that shaft rotate. And then what's this business here? This big pipe is a transfer pipe from the high pressure turbine section over into the lower pressure turbine section, but also this is called an extraction point. And so steam is extracted in many power plants, in most power plants. Some steam is extracted to use feed water heating, to heat the feed water before it goes to the boiler. Okay, and so this section right here is the low pressure turbine section, and it looks like a bow tie, doesn't it? And so the fun fact here that I've said is, see how the steam is admitted in the middle of the section. The steam is flowing in both directions. And the interesting thing there is that steam is running in both directions in order to balance the axial load on the shaft. Because look at the size, look at the huge size of those steam turbine blades in the low pressure section. So that's pretty interesting thing to observe, is the lower pressure sections are often look like a bow tie in order to balance the axial load on the shaft. And then, well, where's the steam go from there? It's going to go down. It's going to go down below the floor here into the condenser. Here's another look at a different steam turbine. Here's the generator, okay, high pressure section. This would be the throttle valve, so that the operator is trying to balance the electric demand with the mechanical output of the steam turbine. So he or she is automatically adjusting this throttling valve to balance the demanded load for the amount of W dot out turning the shaft. Okay, so note here's the low pressure section, and then classically you see that expanding shape. That's what shows you that that's a lower pressure section of the turbine. This is a great view of a rotor that has been removed from the turbine, let's say for maintenance reasons, manufacturing reasons, and so all these sections are on one single shaft, driving the shaft. Okay, multiple turbine sections here. This is a cutaway view of an older type. It is a vintage steam turbine, but still, it's vintage, but still commonly used, still commonly in service. So here's our, this linkage is the throttling valve going into the high pressure turbine section. Coming out of the high pressure turbine is what we call the extraction point, where we're extracting steam once it's been expanded and rotating the shaft. Some of the steam is going for feed water heating, but then we come in to the lower pressure turbine section, continuing to make power. And then here's the outlet that's going to be going downwards into the condenser, all hooked up on one rotating shaft to go to a electric generator. Still widely observed in practice. This also is a vintage steam turbine and generator set, very similar to some of the equipment that I worked with when I was working. And this would be called a back pressure steam turbine. So you'll see that this turbine is not very big, is it? So in the whole scheme of things, here's the generator. The vintage generator is much bigger than the turbine, and that's what signals to me that this turbine is not going to a condenser. It's going. What's going in is going to be high pressure steam. What's coming out of this turbine would be considered intermediate pressure steam, well above atmospheric pressure, and it would be going somewhere to some process where steam heating is needed, some type of manufacturing process. And so the exit pressure of this turbine would be well above atmospheric. Here's a picture of a modern multi-stage steam turbine generator unit. And of course, this would be part of a power plant. It's located somewhere in Europe. And in terms of a sense of scale, look over here. The scissors lift, the industrial scissors lift. So you know what one of those, you've seen many of those in your experience, but that gives you a feel for the physical size of this whole installation, which is going to be high pressure steam turbine, intermediate steam turbine, and then lower pressure steam turbine stages. Just a huge production of electric power. And the generator we can't even see back behind this low pressure turbine section. Let's talk about what the condenser looks like. A condenser is a fairly simple piece of equipment, but as important as all the others. That was a picture of what a condenser looks like, but it's better to get started with this cutaway view sketch. Notice here how, think of the condenser as a large cylindrical vessel. And what's coming in the top of this cylindrical vessel is, is low pressure steam from the turbine, exhaust steam from the turbine. It's going to be at a low pressure. Okay. We've got to condense that steam somehow, and we do using a low temperature heat source in these blue tubes. A little bit more on that in a minute. But these blue tubes they're less, I wouldn't say they're cold. They're probably about at room temperature. Whatever's in that tube, in those tubes, is would be sort of a room temperature water. And so that is plenty cool enough to condense that steam. And out comes the condensed steam because of gravity of this cylindrical vessel. Physically, the saturated liquid drops to the bottom of the vessel, and that's what enables us to collect that water and send it off to the condensate goes to the feed water pump. Now, let's look at what's called the tube side of this condenser heat exchanger. You've basically got cool water coming in, let's say from a river, a lake, or the outlet of a cooling tower. Okay, cool water's coming in into these hundreds or thousands of little tubes. It's coming in, it's going across, so it's in thermal contact with the condensing steam. It makes a U-turn here at the end of the cylindrical vessel. Okay, turns back, and then out it goes. And obviously, it's going to be warmer because you've condensed the steam. These two streams do not mix. The turbine steam does not mix with the cooling water. And so one thing I've shown for this video is how would you, the way you would depict this, perhaps on a sketch, would be a simple two-pipe heat exchanger. Wet steam coming in from the turbine, okay? It's exchanging heat with a cool water source in the blue, going left to right, and then this condensate to the feed water pump, saturated liquid is coming out there. So that could be a way to depict a real world condenser in one of your sketches. But do recognize this is where Q.L exists. This is Q.L. This is a better blown up picture of what the condenser looks like. And so I'm hoping that you'll get a picture of, here's our cutaway sketch with the nice blue cooling water. Here's the photograph. So you can see wet steam is coming in. Look at that. Look at that. It's a square duct coming in. Such a high volume of steam coming in, steam at a pretty high quality coming into the cylindrical vessel. It's exchanging heat with the cooling water. And so saturated liquid water is being collected by gravity in the hot well of the condenser, which essentially is the bottom of the condenser. And so you can see here, look at these two very large flanged pipe inlets. One flanged inlet is for the cooling water going in, and the other flange is for outlet for cooling water going out at a warmer temperature than the inlet temperature. Simple as that. Be aware that for steam power plants, the condenser operates well below atmospheric pressure, well below atmospheric pressure. And so let's do a little example problem. Let's say our cooling water is at 20 degrees C. That's pretty reasonable, 20 degrees C. So we're cooling at 20 degrees C, okay? And we're cooling at constant pressure from a very high quality to no quality, to saturated liquid, all right? So we're cooling at constant pressure. If we know the temperature of our fluid at which it's cooling, can we figure out the pressure? I'd say yes, we can. We go to the temperature table, we go to 20 degrees C and look up the pressure is 0.0233 bar. Well, that's going to be 2.339 kPa, 2 kPa. Wow. So what? Well, the so what is, what's atmospheric pressure? You know off the top of your head now. atmospheric pressure is 100 kPa. And so look at this. So you're condensing at a pressure of 2.3 kPa. Outside of the condenser is 101 kPa. So the condenser is running at a vacuum, a very high vacuum. Condenser running well below atmospheric pressure. Condenser is running at a vacuum. Now, for a lot, not going to spend much time on this, but do be aware that since the condenser is operating at a vacuum, do you see that for all these flanged inlets, air is going to try to get into that condenser. Air tries to sneak in wherever it can through cracks in the flanges. That is bad for condensing because you can't condense air. So if you end up getting your condenser full of air and not steam, your plant is going down. And that's why some smart engineer came up with what's called a steam jet air ejector. And this is, and you see in the sketch, it says 2 ejector vacuum system. That's what we have here is this converging, diverging nozzle takes in steam, perhaps some of that extraction steam. It creates a very low pressure. Here's where my extraction steam goes. I pointed wrong with my cursor. Extraction steam comes in here, creates a very low, because of high velocity, it creates a low pressure and it tends to pull out any air from the condenser. So it's called a steam jet air ejector. And the reason you have one of these in real world situations is because the condenser is operating way below atmospheric pressure. So let's see. It says steam jet air ejector removes non-condensable gases. So that is a real world problem in condenser operation. We've got the fourth piece of equipment, the feed water pump. This is a picture of a real honest to goodness boiler feed water pump. And in previous videos, I've shown a lot of pictures like this, haven't I? I've shown, here's how you draw your sketch, basic centrifugal pump. Here's what a basic centrifugal pump looks like with one impeller or rotor. Okay. It does turn out that for power plants, you're operating at such a high pressure, your boiler runs at such a high pressure in order to deliver high pressure superheated vapor to the turbine. One rotor is not enough to increase the pressure of the feed water enough. And so in the real world of feed water pump needs, we are always running multiple stages of centrifugal pumps. And so this is an example of what a multiple stage centrifugal boiler feed water pump looks like, even though your sketch can just look like the sketch you've been trained to do, the centrifugal pump schematic. Let's see how many we have. Let's see how many stages we have here of impellers. We've got, this would be the inlet because I see the impeller size is shrinking down. That means specific volume is decreasing some. We've got 1, 2, 3, 4, 5. We've got 5 stages of rotors to develop that high pressure feed water. Over here on this one, you can look carefully and you sort of see some stages here. I see 1, 2, 3, 4, 5 stages of this feed water pump casing. Okay. And then here also, this shows you the electric motor drive needed to drive a multi-stage centrifugal feed water pump. And so typically for motor-driven feed water pumps, this would be the arrangement you see with the electric motor coupled up with the feed water pump shaft. Now, if you say, look, I'm eager to see how the numbers shake out. I've gotten a homework problem and I want to see now how do I work through a problem. So on my playlist, homework solutions playlist, problem 816 is a fully worked out analysis of a Rankine cycle with irreversibilities in the turbine and the pump. Runs 51 minutes. Okay, I hope this has helped you see, at least give you some idea of what these pieces of equipment look like. The basic purpose of a steam power plant is to provide a continuous 24/7 source of electric power. And what were those basic components? I hope now that you've got them in your head so you can create your sketch without a cheat sheet. You got a boiler, a steam turbine, a condenser, and a feed water pump. So that's it. I'm going to be interesting to find out how long I took on this video. I always enjoy talking about the equipment and communicating to folks. What does all this equipment really look like? And I know that in my case, I was fortunate enough to have had a power plant tour at Virginia Tech, and even that tour really got me interested in learning more about how do I analyze these big, huge pieces of equipment. So there you go. And I hope this helps prepare you to do well in your analysis in Chapter 8.